Okay, I hope everyone can hear me. So it's a pleasure to have Anand with us today. Uh, he's coming to us after doing a PhD at MIT with our former faculty, Aram Harrow. He's now at the Institute for Quantum Information and Matter at Caltech, where he's thinking about his quantum information, quantum complexity theory, quantum algorithms, and connections to lots of other things in CS and physics. Anand won the Best Paper Award at Fox 2019 for his work on quantum interactive proof systems. And since then has done even more amazing work in the area, some of which we'll hear about soon. And then one other thing, I think he has the distinction of being the only colloquium speaker to have a gold medal in the International Physics Olympiad. We've had an IMO gold medalist colloquium speaker more than once, but I think this is the first time for physics. So without further ado, let me hand things over to Anand, except one more thing. If you have a question, just raise your hand in the chat and then I'll call on you. Okay, so Anand, you can take things.
Okay, well, thanks for the very generous introduction, and thanks everyone for coming to attend this talk. So I'm going to tell you about some work on interactive proofs and quantum entanglement, which James alluded to, but just to sort of set the context, I want to start by telling you a little bit about complexity theory and quantum computing and where I think this all fits in. So, okay, complexity theory, as you may have come across it, sort of really what it's all about is understanding, the power of various resources to solve computational problems. Like you may think of complexity theory in terms of these crazy Venn diagrams that everyone draws, like, you have P and NP and all these other complexity classes. But ultimately what these things are trying to encapsulate are certain resources that we want to understand. Like what's the power of say time or space or interaction or randomness when given to a computer and used to solve computational problems. So complexity theory is an old field that has been already, it's had great successes. So we have ideas like NP completeness that can explain why some problems are hard and other problems are easy for our computers. There's this other, other notions. But ultimately, it's a beautiful mathematical theory, but ultimately it is based on a certain, I'd say idealization of physics. And why is that? Well, it's because ultimately when you try to come up with these models for like where these computational resources come from, they come from some sort of notion of what a physical computer would actually do. So for instance, we care about the class P because we think it models how long, how like a physical device that runs in polynomial time would behave. So, there's this connection sort of hidden underneath it between complexity theory and physics. And the complexity theory that we know and love is sort of based on classical physics, as are all the computers that we normally work with on a day-to-day basis. So over the last few decades, people have been sort of realizing that if you try to base a theory of computation on quantum physics, which we believe is the correct set of physics to describe the universe we live in, you get sort of quite a different theory out. And we've seen that quantum computers should be able to do things that we don't believe that classical computers can do efficiently. So for instance, Peter Shor and Shor's algorithm demonstrated that a quantum computer could efficiently factor a large number, whereas we don't think a classical computer can do that. Another application that actually Richard Feynman was, I think, the first to really point out is that a quantum computer could efficiently simulate quantum physics. So things like, chemical reactions involving many atoms or molecules behaving under the laws of quantum mechanics. This is a problem that's both of practical relevance and is in general hard for a real computer to solve. Other examples are known of say cryptographic primitives that you can implement with a quantum computer that are impossible classically, or at least under the kinds of security assumptions that you want to make for the quantum computer. So these quantum computers seem to be very exciting theoretical constructs, and in the last few years we've sort of seen that more and more they're becoming experimental reality as well. So we've had this long sequence of works building up our experimental capabilities, and now we're at the point where people can build devices that have say like on the order of 50 qubits and can actually do tasks that we believe are computationally difficult. So you might have heard of say the Google quantum supremacy experiment, and that's an instance of that. So quantum computing is an area that's, now has like a well-established theory. It seems to be, coming into, becoming a reality as well in practice. And so it's really, a relevant question to understand how does computational complexity theory behave in the quantum realm? How does it handle quantum computers? So this is where quantum complexity theory comes in, and this is the field that I work in. So quantum complexity theory is relatively young as a field, but it already has achieved some successes. So, we already have sort of quantum analogs of some of our favorite classical complexity classes like P and NP. And we have some sort of an understanding of where the problems we care about fit in this quantum complexity framework. But there's still many puzzles that remain open, a lot of them related to trying to understand how quantum computers are qualitatively different from classical computers. So in this talk, I'm going to tell you about one such puzzle and our work towards resolving it. And it's about a particular classical complexity class and how it interacts with a uniquely quantum computational resource. So in this slide, I'm just going to give you, like the one slide summary for the talk. So if you want to fall asleep after this, that's fine. So what's this talk going to be about? Well, it's going to be about a particular quantum complexity class called MIP star. So the way that class is defined is by taking a classical complexity class called MIP, and I will explain sort of what it means and why it was relevant in classical complexity theory. But for now, you can think about it as sort of a fancy version of NP. So this is a class that shows up in much of the modern theory of NP hardness for things like approximation problems. So it comes from taking this fancy version of NP and augmenting it by a resource that's unique to quantum mechanics. This resource is called entanglement. And so what's the question about MIP star? Well, the question is sort of where does it lie in our complexity landscape? And just to show to you the possibilities, I've drawn this little diagram here. So this diagram on the left is sort of a compressed version of the ones I showed before. So down here on the left are sort of all the complexity classes that we normally consider in complexity theory. So these are classes that consist of problems that are computable. So they're solvable by a Turing machine in some amount of time. It's just a question of, how much time exactly do you need and how much space and so on. So that's here on the left. So you have things like P and NP and also bigger classes like polynomial space and non-deterministic exponential time and so on. On the right of this diagram, I've shown a class called RE, which stands for recursively enumerable. So if you don't remember the definition of this class, the important thing about it is that this is the class for which the halting problem is the complete problem. So as you may recall, the halting problem is an example of an uncomputable problem. So a problem where there's no algorithm to solve it. And so, RE is like a class of these uncomputable problems. So this is sort of a landscape of complexity classes or computational problems. And the puzzle about MIP star, the big open problem here was where exactly does MIP star lie in this line? So the best lower bound that people could show prior to our work is that MIP star is at least as powerful as its classical counterpart in this NP on steroids class, which is over here. And it's at most as powerful as this class containing the halting problem. But where it lay was unknown. So the big result that I'm going to tell you about is that in fact, we can show that MIP star is equal to RE, that this quantum complexity class obtained by taking a very natural classical class and augmenting it by this natural quantum resource suddenly jumps up in power to be, containing uncomputable problems. So I'll try to explain, sort of where that comes from and what that means in terms of, the power of quantum mechanics and so on. But I want to make another remark is that, in addition to solving this complexity problem of what the power of this class was, this work also has some implications for the foundations of physics and also for pure math, for some questions related to the theory of operator algebras. So I'll get to this at the very end of my talk, so there's like a broader context here beyond complexity theory as well. So okay, so that was sort of the outline of the talk in a nutshell. So for now, the remainder of the time, I'm going to split it into a couple parts. So the first thing I'll do is I'll explain to you just what this classical class MIP was and why it was a natural thing to study, what its significance is. And then I'll tell you about how quantum entanglement modifies the picture, and then I'll explain, the techniques that we use to prove this result, and put it in context with this, with these physics and math problems. Okay, so to explain MIP, I need to start with a more basic concept that's proved extremely useful in complexity theory, and that's the notion of a proof system. So a proof system is sort of describes an interaction between two parties. So here we have a party called the prover. So the prover is assumed to be a being that is computationally unbounded. So we don't place any restrictions on its computational power. However, it is untrustworthy. So the prover might claim certain things, that the solution to some problem is such and such, but you have no way of knowing whether what it's saying is actually true. On the other hand, we imagine there's a party called the verifier, whose goal is to solve some computational problem, but the verifier itself does not have very much power, so it's computationally bounded. So in this, basic example is to have a verifier that can only execute polynomial time computations. So the idea of a proof system is that by interacting with this untrusted prover, it can be possible for a verifier to learn the answer to some problem that it wouldn't be able to solve on its own. And the most basic example of that is just the complexity class NP. So you may have seen a couple of different definitions of it, but the definition that I like the most is, in terms of a proof system, a problem is an NP if it has a proof system where a prover can write down a proof and then send it to the verifier, and then the verifier can check that proof. So let's do an example to explain what this means concretely. So an example of a problem in NP, so all the problems in NP are by definition decision problems, so that you want to give a yes or no answer. An example of such a problem is graph coloring on a graph. So given a graph of n vertices, you want to determine whether the graph is 3-colorable. So that means that, is there a way to color every vertex with one of 3 colors such that every edge has, both of its endpoints having different colors? So why is this problem in NP? Well, it's an NP because if the answer is yes, then there's a way that for the prover to write down a proof that the verifier can check that certifies that the answer is yes. And if the answer is no, then there's no proof that the prover can write down that will convince the verifier to say yes. So how does that work? Well, the proof is just a coloring of the graph. So for instance, if I take this graph over here, if I ask, is this graph 3-colorable? Turns out the answer is yes, it is 3-colorable. And the way the prover can certify that to the verifier is by writing down a coloring, say this one, and sending it to the verifier. So then the verifier could take this coloring and then just go through every edge one by one and check that, indeed both endpoints of the edge have different colors and the total number of colors being used is 3. So that's a valid 3-coloring, and therefore the graph is 3-colorable. Similarly, in the no case, so say I start with a graph that's not 3-colorable, so that's this one over here, there's no way for the prover to falsely convince the verifier that it's 3-colorable. Because whatever coloring that the prover claims, by the fact that this graph is not 3-colorable, that coloring will have a flaw in it, and the verifier can detect it because it will just iterate through the edges until it finds, say, this edge over here, where both endpoints are green, and say this is an invalid coloring, so I'll reject. Okay, so I hope this, this definition was clear. So this is the most basic example of a proof system. This is the class NP. So to get up to MIP, I'm going to tell you how to augment this by a few bells and whistles. So the first thing that you might imagine doing is, in the NP proof system, basically what happened is there was just sort of one round of interaction. There wasn't even any interaction per se, in that what happened is the prover would write down a proof and then the verifier would read it, and that's all. You can imagine a richer proof system would be one in which the verifier can issue challenges to the prover and get back responses, and then issue more challenges and get back more responses, and so on. And then at the end of some sort of adaptive interaction can decide whether to accept or reject the prover's claim. So this class is called IP, standing for interactive proofs. And it was shown in the 80s that actually IP is more powerful than NP. So adding this ability to do interaction lets the verifier be convinced of solutions to a richer class of problems. So the result that was shown is that IP is equal to P space, the class of polynomial space. So an intuition for what's going on here is that the relation between IP and NP is like the relation between an oral exam and a written exam. So in an oral exam, it's much easier to seek out the areas that the examinee doesn't know very well and like find out their weak points, whereas this is harder in a written exam. And so what happens is that the verifier has a lot more power to detect falsehoods. So if the prover is trying to falsely claim that the answer to some problem is yes, then the verifier can adapt its questions until it detects an inconsistency or a flaw in the prover's claim. So that's where the source of this extra power comes from. Okay, so that was the first modification. Now to get up to MIP, I have to add a further enhancement to this class. And here's what it is. So instead of having just a single prover, I imagine having two provers. So how is that going to work? Well, here I have a diagram. I've just labeled the provers Alice and Bob. And now the rules I'm going to set down are that beforehand, the provers will be allowed to coordinate to prepare whatever strategy they want. So they can meet up and they can flip random coins and write down the results of those coin flips on a piece of paper. They can agree to certain answers for certain questions and so on. They can do all of this. But then once the interaction with the verifier starts, the provers will be separated. So there'll be like a wall or something between them. They won't be allowed to communicate. So now what will happen is that the verifier will get to separately interrogate the two provers. So it'll be able to come up with a random challenge for Alice and a random challenge for Bob. And Alice will have to respond to the random question that the verifier sent without knowing what question Bob received. And likewise, Bob will have to come up with an answer to his question without knowing what question Alice received. And at the end, the verifier can observe both the answers and do some sort of, decide whether to accept them or reject them. So this is, an instance of like a one-round multi-prover protocol. You could imagine multiple rounds of this, but actually for my purposes, it'll be sufficient to consider just one round. So it was shown by Fortnow and Lund in the 90s that actually this class MIP of multi-prover interactive proofs is more powerful still than IP. So the result that was shown is that MIP is equal to NX. NX stands for non-deterministic exponential time. So what this means concretely is that in this model, the two provers can convince a verifier that an exponentially big graph, a graph of size 2 to the n, is 3 colorable. So remember that in NP, a single prover could convince a verifier that a graph of size n is 3 colorable. So here we're dealing with problems that are exponentially larger. And so where did all of this extra power come from? Well, really it's the assumption that you have that the two provers are not allowed to communicate. So it's the non-communication that's the result of this, that's the cause of this power. And the idea is that the non-communication gives the verifier a lot more leverage on the provers. It makes it much easier for the verifier to detect inconsistencies if the provers try to falsely make a claim that a graph is 3 colorable, because it can separately interrogate them and see whether their answers fit together. And that's the intuition that goes behind this, this protocol that BFL designed. Okay, so we've seen this class. I hope that the definition of the complexity class makes sense. And I've shown to you that it's very powerful and everything, but it does seem like a highly contrived complexity class. So why would anyone care about these weird multi-prover interactive proofs? Well, it turns out that even though they look very contrived, they're actually have proven us to be central to many developments in complexity theory and beyond, sort of over the last couple of decades. So maybe more on the pure complexity theory side. Why was this class MIP important? Well, it turns out that the techniques used to show these protocols led very directly to an important theorem in complexity theory called the PCP theorem. Why was the PCP theorem important? Well, that in turn was sort of led to a whole slew of hardness of approximation results for combinatorial optimization problems for things like max cut or max 3-sat and so on. So to put that in concrete terms, what that means is sort of, if you consider a problem like max 3-sat. So max 3-sat is, given a SAT formula, I want to figure out what's the maximum fraction of the clauses I can satisfy. Then we know from the basic theory of NP hardness from the Cook-Levin theorem that determining whether I can satisfy all the clauses is NP hard. So that's, a fraction of 1. And you can show by some some basic arguments that satisfying a 7/8 fraction of the clauses is easy just by sort of picking a random assignment. But for any fraction in between, it was sort of unknown how hard the problem was. And the PCP theorem tells you that, in fact, any fraction between 7/8 and 1 is still NP hard. So it shows sort of like the strongest hardness you could hope for this problem. And this holds not just for max 3 set, but for many other combinatorial optimization problems. So that's on the complexity theory side. On the maybe slightly more practical, or I should say like cryptographic side, the ideas behind these MIP protocols were very important in designing protocols for delegated computations, in the setting where you want to have some server do a computation for you and be confident that the server did it correctly. Also, the notion of a zero knowledge proof was closely related to the motivation behind these MIP protocols. And I think they've been important in constructions of these. So zero knowledge proof is one where the prover can certify that they've solved a certain problem, but not divulge any further information about the nature of the solution. Actually, some of these ideas have been put into practice in recent years. So there's actually some companies working on things like blockchain and cryptocurrencies that are really coding up these PCP constructions and these MIP protocols in practice. So these are just some logos of companies that do this. So there's really a wide spectrum of different applications of these ideas. Okay, so hopefully I've convinced you that this class MIP, although it looks kind of weird, it's actually important to understand its power. So now I'm going to switch gears and tell you about how this all changes in the quantum world. What happens when I take MIP and combine it with quantum mechanics? So the complexity class that you get when you do this is called MIP star. And let me explain to you what the definition of it is. So it's going to be sort of the minimal, reasonable quantum modification of MIP. So, in MIP, remember the sort of the philosophy of these interactive proof classes is that the verifier should be bounded and the prover should have a lot of power, but we want to keep the verifier as weak as possible. So we'll maintain that here. We'll say that the verifier will remain classical. It's still interacting classically with these provers, but now, we're going to allow the provers to not only computationally do whatever they want, which they could do before. We'll also let them do, physically whatever operation they want to do in a quantum world. So there'll be quantum provers with quantum physical capabilities. And so what does that mean in terms of what I said about, how the provers can set up a strategy, but then they can't communicate afterwards? Well, the rules are going to be that the provers can meet up beforehand and share a quantum state of whatever size they want. So they can prepare however many qubits they want in whatever quantum state they'd like and distribute them amongst themselves. But then once the protocol starts, just as before, we're going to have them, separated by a wall or something, and they won't be able to send signals to each other. And so if you ask, is that actually, compatible with quantum mechanics? The answer is yes. So it actually follows from the speed of light barrier that you can set up a protocol like this where you can certify that two parties don't communicate with each other. So anyway, that's all right. So you can still say that Alice and Bob don't communicate, but what we'll allow them to do is they will be allowed to perform local operations, including measurements, on the qubits that they distributed amongst themselves in advance. So, when they prepared their strategy, Alice got some share of the qubits, Bob has some share of qubits. And then during this interaction, even though they can't communicate, Alice will be allowed to measure her share of the qubits and use that to help her determine an answer to the verifier's question. And similarly for Bob. So this is the basic setup that we're going to study. And now the whole question here is, how does MIP star differ from MIP? And really, that boils down to how does sharing this quantum state that you can prepare in advance, how does that differ from what you could do classically, where you'd share say like random bits or deterministic bits or some sort of like pre-shared string? So really, it's trying to understand what the power of the shared quantum state is. Okay, so at first you might think, well, maybe it shouldn't make any difference at all because the provers still cannot communicate, that's unchanged even in quantum mechanics. So why would this pre-shared quantum state make any difference? Well, it turns out that there's a phenomenon called quantum entanglement that can have very interesting effects even when you don't have any communication. So this is, I think, a very interesting part of the story, because entanglement was discovered sort of long before these ideas of interactive proofs showed up in computer science. And yet, the ways that physicists thought about it are actually very similar to the ways that computer scientists think about interactive proofs. So, so I can't give you, a rigorous like physical definition of what entanglement is, but just at a very high level, entanglement is like a kind of quantum version of correlation. So, classically, if you have random variables, that are, say, 0, 1 valued, you could imagine that, say, they're both in the 0 state, or they're both equal to 1, or they could be in a probability distribution where, with half probability they're equal to 0 and half probability they're equal to 1. So that would be an example of two correlated random variables. Now, quantum bits or qubits have a similar sort of property that, they could both, say, be in the 0 state or both in the 1 state, but they could also be in what's called superpositions of those two states. So for instance, here I've written something called the EPR state, which is an equal superposition of both qubits being 0 and both qubits being 1. So these sorts of things, which look like classical correlations, are called entangled states. It turns out that these entangled states can do things that even classical correlation or classical shared randomness cannot do. And this was discovered sort of back in the 60s. So this work of John Bell showed that entanglement could give two provers in a interactive proof setup just like this a quantum advantage over any classical provers, which classical shared randomness. So I think it's instructive to go through Bell's example just to give you a flavor for how these, how this entanglement can be used. So I'll go through it with you. So this is something called the CHSH game. It's a task that's just like one of these MIP protocols. You have a verifier and two provers, but it doesn't encode any computational problem. It's just a very small, constant-sized object. So the way the task works is just the verifier generates a random challenge for each prover, and that random challenge is just a single bit. So the verifier will send Alice a single bit that's either 0 or 1, and Bob a single bit that's either 0 or 1, and it will expect to get back an answer that's also a single bit. So either 0 or 1 from Alice and from Bob. And then the verifier will accept the answers, or say that the provers have won the game, if they satisfy a certain condition, which I've written in this table here. So the thing to know about this condition is that really the verifier is going to ask that Alice and Bob either return the same answer or different answers, depending on their questions, in the following funny way. So the possibilities of the questions, there's 4 possible pairs of questions, right? Because each player can get a single bit. And for 3 out of the 4 cases, I'm going to demand that Alice and Bob respond with the same answer. But for the 4th case, this case where Alice and Bob both get the question 1, I'm going to demand that Alice and Bob respond with different answers. So now if you think about this and you say, well, if Alice and Bob are classical and they just share, say shared randomness or whatever else, they could coordinate on in advance, how would they succeed in this game? Well, there's no way for them to succeed with probability 1. And why is that? Well, if you just think about, if you're Alice and you receive the question 1, you don't know whether you're in the case where you have to agree with Bob or the case where you have to disagree with Bob. There's just no information that can tell you that. And so there's no way you can with certainty respond the correct way. And so actually the best that you can do classically in this game is you can win with the probability of 3/4. So for these, 3, if Alice and Bob say always output the same answer, then they'll always succeed in the equality cases, and in the inequality case, they'll lose. So that's where you get the 3/4 from. So this is what you can do classically. And now the amazing thing about entanglement that Bell discovered is that using a particular entangled state, this EPR state that I mentioned, and measuring it in a certain special way, you can succeed in this task with a probability of 85%, something that's strictly greater than 3/4. So somehow, even though Alice cannot, get any communication from Bob, she doesn't know what Bob's question is, she can arrange to produce measurement outcomes that are magically correlated with Bob's outcomes in such a way to succeed in this task with a better than classical probability. Okay, so this is how entanglement can give you a quantum advantage in these sorts of tasks. So okay, what was the point of this example? Well, there are a couple of points I wanted to make from it. One is that this is like a very surprising phenomenon. Like sort of a priori, if you just like if I just gave you this definition of what the model looks like, you wouldn't expect something like this to happen. And so there's a potential for quantum mechanics to yield, interesting behavior in this MIP setting, this multi-prover setting. The second 2 points I want to make are that you can also sort of interpret this as like telling you that interactive proofs of this kind, in the quantum world can give you like the kinds of insights that you can't achieve classically. So one thing that you could say is that, if you think about this CHSH game, if you play it with two quantum provers and you observe that they're, succeeding with a probability greater than 3/4, then that's a certificate that the provers are doing something physically that's not describable by classical physics, right? Because otherwise they'd be limited by 3/4. And so these, interactive proofs in the quantum world are actually can certify not just the answers to computational problems, they can also certify physical properties of the actions that the provers are taking. Like they can certify that the provers are preparing, a quantum state and doing something non-classical to it. So that's like a totally new power that you don't have classically. And it's sort of thing that you might find useful, in the real world when you're designing, a quantum protocol that uses some devices that maybe you don't trust were manufactured correctly, or maybe you think the devices have been hacked by someone. This kind of protocol might give you confidence that the devices are doing the physical actions that they're supposed to do, because they can certify this to you by running one of these interactive protocols. So those are sort of the lessons of the CHSH game, and I hope they've convinced you that this class MIP star could be very interesting. In addition to the reasons why MIP on its own was interesting, but it turns out there's also for these sorts of reasons, it's also very hard to say anything interesting about MIP star. So I want to explain sort of why it's technically challenging to say anything about the power of this class from two directions. So if you want to understand a complexity class, you might try to upper bound it, say that it's at most as powerful as something, or you might want to lower bound it, you want to say it's at least as powerful as something. And it turns out that both directions are tricky for MIP star. So first I'll start with the upper bounding direction. The key problem when you sit down and try to prove an upper bound on MIP star is that we just don't understand this phenomenon that showed up in the CHSH game very well. We don't know in general, what sorts of quantum states can give you an advantage in these kinds of tasks, and sort of also how many qubits you might need to achieve an advantage. So the CHSH game was nice because I could, show you like a very concrete quantum state that realizes this advantage. But it turns out that there's very similar games, like there's this thing called the I3322 game, where we actually just don't know what the correct quantum state is. Like we have a family of quantum states that do better and better, but there doesn't seem to be any clear limit, and we conjecture that you actually cannot, achieve the optimum with a finite size quantum state. So in general, we have a very poor understanding of how many qubits or how big of a state the provers might need to attain a quantum advantage. And what that means in complexity terms is that if you want to put an upper bound on the power of these quantum provers, you need to come up with some algorithm that can sort of simulate what they do. And the best algorithm we can come up with is just a brute force enumeration over anything that they could possibly do with, say, 0 qubits, with 1 qubit, with 2 qubits, and so on and so forth. And since we don't know, how many qubits the provers might need, we don't know when this enumeration will stop. And when you translate that to complexity classes, what you get is MIP star contained in this class RE, the class characterized by the halting problem. So that's why the upper bound is difficult. Why is and indeed, I'm going to show you that the upper bound is actually tight. So there's actually no better upper bound you can prove than RE. So I'll have to move now to the lower bound. Okay, so we can't, show a better upper bound in this class. Maybe we can at least show that MIP star is harder than something else. It's more powerful than something else. In fact, the place you might want to start is, well, at least MIP star should be as powerful as its classical counterpart, right? Because we took a classical complexity class, we just augmented it by adding this power. I mean, that cannot possibly decrease the size of the complexity class, right? Well, it turns out that intuition is also dangerous. And the reason is the following. So whenever you have one of these interactive proof systems and you augment it by giving the provers more power, that can work in two different ways. So giving the provers more power gives them the ability to certify more, computational statements because they can do more things. But it also increases their ability to cheat. It makes it easier for them to falsely claim that they've solved a computational problem and fool the verifier into believing that. And it's really unclear which of these effects is stronger. And sort of a priori, we could have thought that MIP star was less powerful than MIP. And indeed, there are examples known of MIP protocols that don't work when you allow the provers to have entanglement. So the lower bound that was shown by Ito and Vidic in 2012 was, you can indeed show that MIP star is as powerful as MIP, but it's technically quite difficult. So you have to take one of these MIP protocols and carefully analyze every step to show that entanglement doesn't let dishonest provers cheat. So in our work, the work I'm going to tell you about, essentially what we did is we improved this lower bound to match the upper bound. And the way we did that is we had to balance these two things delicately against each other. We had to show how two provers could use the entanglement to do new things that classical provers cannot do, but also how a verifier could prevent them from cheating. How a verifier could certify that the provers are only using the entanglement in approved ways, in certain specified ways. So that's sort of the approach that I'm going to describe. So the first thing I'll tell you about, the first result, is a generalization of the CHSH game to a game that lets a verifier test that provers share very large amounts of quantum entanglement. And then in the second part, I'll tell you how that was used to show this equality if MIP star equals RE. And then I'll conclude with the connections to physics and math. Okay, so let me get into the first set of results. So to explain what the results are, I have to tell you one more property of the CHSH game that's actually very useful. So I told you earlier that, you can think of the CHSH game as sort of an interactive proof of a physical property, right? So it's a proof of the property that the provers are doing something non-classical. Well, it turns out that actually, if you analyze the CHSH game carefully, it shows something quite a bit stronger. So this is discovered, I guess, in quantum information in like the late 80s and the early 90s, that the CHSH game certifies a unique quantum state and a unique set of measurements. So what does that mean concretely? Well, if you play this game with two provers and you observe that they're succeeding with a probability that's close to the optimal success probability, then you know that not only are they using quantum mechanics, but they're actually using that particular quantum state that I wrote down, a few slides ago, or something that's very close to it. And the measurements that they're applying to compute their answers have to be close to the particular measurements in this unique optimal strategy. So what you get is that this game can behave as actually sort of a classical leash for a quantum system. And that's a quotation from a title of a paper. And this idea is very useful in designing quantum protocols, that you can force these provers to do things for you by playing one of these games and observing for success, observing success in the game. So our goal here will be to generalize this by scaling up the CHSH game into a family of games that has the same kind of, very tight, rigidity property, but not just for the EPR state, which is a state on 2 qubits, but for, a state on n qubits. So the state we'll consider is the state that just consists of n copies of this EPR state. And we want to do that as efficiently as possible. So we want the verifier to have to do as little work as possible to verify this large this large physical state. So I can't go too much into the techniques that we use for this, but I'll just say at a high level sort of what a first attempt was and why that didn't work. So the first thing you might try is you might want to just say the CHSH game works for certifying one copy of this EPR state. If I want to certify n copies, why don't I just play it n times in parallel? And so indeed you can do that. So this is actually something we analyzed, and this is joint work with Matt Kudron. We looked at something slightly closely related to CHSH called the magic square game, and we analyzed the parallel repetition of that. And you can show some sort of bound that a nearly optimal strategy has to use a state that's close to n EPR pairs, but the bound is not really tight enough to be usable. And there's an intuition behind that, which is that this is a quote of John Preskill that I really like, that sort of the way quantum states work is that if you try to read them one qubit at a time, you don't learn anything about the global information in the state. Like there's a lot of information in quantum states that's made out of like global correlations across all the qubits. And so, this approach of like, playing one, taking this test in parallel, repeating it and analyzing it one repetition at a time is sort of doomed to failure. So we had to, use some ideas that are sort of more clever. And what we ended up doing is to use ideas that really came from the classical literature on the PCP theorem, this concept of local testability. And so what does local testability mean? Well, it says that often, it's the case that if you have some sort of global object that's supposed to have a global structure in it, you can detect this structure by just making queries to the object at a few random points. And like my favorite example of this is if you have a function over the Boolean hypercube, so over 0, 1 to the n, and you want to detect whether that function is a linear function. So, f of x is just the inner product of this binary string with some fixed string. Well, it turns out that you can detect this by just querying the function at 2 random points and their sum, and checking that it satisfies this linearity relation. This is a classic result of Blum, Luby, and Rubenfeld. And what they showed is that if you just do this check of this linearity property at a randomly chosen pair of points, and you observe that it holds with high probability, then the function globally has to be close to being a linear function. So this is the sort of idea that we wanted to generalize to the quantum case. We wanted to detect some sort of global structure in a big quantum state by just probing it with a few randomly chosen measurements. And there's some additional challenges in the quantum case, which is that we don't have direct access to the quantum state. We only have access mediated through the prover. So we can ask the prover to do a measurement for us. We have no idea whether the prover did it correctly. But anyway, these challenges can be overcome, and sort of the results we came up with are, these are 2 joint works with Thomas Vidic. So in the first joint work, we actually showed a very precise generalization of this test for linear functions to quantum states, which gave us a protocol where a verifier could check that 2 provers have n copies of this EPR state using only n bits of communication. And that was already, useful for complexity theory. It led to improvements in delegated computation protocols. So it's an exponent in one of these protocols went from sort of like n to the 8,000 down to basically n, thanks to using this test. But we were able to further improve this by importing some more ideas from quantum information and also classical local testability and error correcting codes, in particular the idea of the low degree test and the low degree code, to come up with a test where a verifier can certify that 2 provers share exponentially many copies of this EPR state using only a polynomial amount of communication. So now this is the test that's going to be one of the main tools in the second part, which is how do I show that MIP star is equal to RE? Okay, so now let me just very quickly refresh your memory. So remember we said that we wanted to improve this lower bound on MIP star. We wanted to go beyond the classical lower bound. And to do that, we needed to design a protocol where the verifier can force the provers to use a lot of entanglement to do something that they couldn't do classically, but also to only use it in certain approved ways, right? To only use it in the way that the verifier wants. And that's exactly the power that you get from this test for EPR pairs that I mentioned on the previous slide. So then the question is sort of just, okay, we have this kind of test, but how do we fit it into a computational framework? How do we design a protocol for some, some problem that we want to solve? And so there's sort of like 2 works that we have in this direction. So the first work is joint with John Wright. And so this is the paper in Fox. And so what we showed is that there's a way to combine this, this test for EPR pairs with a certain idea called compression that I'll explain on the next slide, to show that a protocol for MIP star that can solve the graph coloring problem on a graph of doubly exponential size. So in complexity terms, this shows that MIP star contains non-deterministic doubly exponential time. So just to remind you, classically we had MIP is equal to NX, so it's equal to this class that solves graph coloring for a singly exponentially large graph, and so that already shows you that MIP star is strictly bigger than its classical counterpart. And then in the second paper, so this is with joint work with Zhengfeng Ji and Thomas Vidic, and John and Henry Yuan, we extended sort of the ideas from here to actually go all the way up to RE. So we were able to show that we were able to show that actually MIP star is equal to RE by designing a protocol for the halting problem. So let me explain to you sort of at a super high level what the ideas are that went into this work. So how did we get from a test for entanglement to protocols for these, crazy computational problems? Well, the idea is that essentially what we're going to use the entanglement to do is the following primitive. It's something we call verifier compression. And so the idea is really, we're going to use the entanglement to take the work that a verifier would do in one of these interactive protocols and offload it all to the prover. Make the prover do that work for us instead of having the verifier do it. So concretely, how will that give us, say the conclusions I claimed on the previous slide? Well, how would I get, say, the NEX conclusion, the doubly exponentially big graph? What I could do is take a protocol, for graph coloring of size 2 to the n. So it's a well-known classical thing. Scale it up by an exponential factor. So wherever I see an n, I replace it by 2 to the n. Then I'll get a protocol for doubly exponentially big graph, where now the verifier has to do exponential amounts of work, right? Because I scaled everything up by an exponential factor. Then I'll apply this verifier compression primitive and take all this exponential work that the verifier was supposed to do and offload it to the provers. Now I'll have a new protocol where the verifier only does polynomial amounts of work, but can certify this doubly exponentially big problem. Okay, so that's what compression is supposed to do. And then how does it actually work? Well, the key idea behind compression is that, as I said, we want to make the provers do the job of the verifier. And really, if you think about it, the bottleneck in the tasks that the verifier has to do is generating these random questions for the prover. That's actually the hardest task that the verifier has to do. It's the task that's hardest to delegate to a prover because it absolutely has to be done correctly. If the provers have any influence on the probability distribution over which the questions are sampled from, they can easily bias the questions so that they'll only be asked, easy questions which they know the answer. And so the way we're going to offload that work to the prover is have the provers use measurements of a quantum state to generate these random questions. So concretely, the way this will work is that to simulate an exponentially bigger verifier, we'll ask the provers to share an exponential number of these EPR states. We'll check that they have them using the protocol that I mentioned a few slides ago, and then we'll instruct them to measure these EPR states in a certain way, and then such that the distribution over measurement outcomes will match what a much larger verifier would have generated in terms of questions. So this whole procedure of measuring this entangled state and generating these random outcomes perfectly simulates what a much larger verifier would have done. So that's how you can compress this larger verifier and then offload all of its work to the provers. So that gives you this doubly exponential result. And then, at a very oversimplified cartoon level, the way you get up to RE is by iterating this. So you sort of compose this idea with itself. You ask the provers to simulate an exponentially bigger verifier that in turn simulates a doubly exponentially bigger verifier and so on. And if you take the sort of limit of this construction in a certain way to make this precise, you need to use something called the Kleene recursion theorem. You can show that you can design a protocol for the halting problem in MIP star. Okay, so now to conclude, I'm going to wrap up by telling you sort of the implications of this complexity result for math and physics, and then a little bit about some future work that I think is interesting. So what are these implications for math and physics? Well, they both go through a certain problem in the foundations of quantum information called Tsearelson's problem. So what is Tsearelson's problem? Well, it's actually a problem related to just mathematically defining this notion of quantum entanglement or quantum non-locality. So it turns out that when I mentioned entanglement, there was a certain subtlety that I brushed under the rug, that there's actually two sort of different mathematical sort of axioms you could write down to define this notion of entanglement. The one that's sort of more standard that I implicitly assumed throughout this talk is called the tensor product model. This is a model where two parties have like their own state spaces, and the global state space is the tensor product of them. And actually, in showing this upper bound that MIP star is in RE, you implicitly assume this tensor product, because when I talk about qubits, the qubits only make sense in a tensor product world. Now, it turns out there's another model you could define called the commuting operator model. This one is sort of more naturally motivated from certain physical theories, like quantum field theory. And in this model, you could define an interactive proof class, but it would have a different upper bound. The upper bound you can show is this class called co-RE, the complement of RE. So if you don't know about these classes, the only important thing about them is that the Venn diagram looks like this. So they have an intersection, but they're not equal to their intersection. So Tsearelson's problem is essentially, is there some sort of experimental test that can distinguish between the tensor product world and the commuting operator world? So this problem is, very interesting just from a physics point of view. Like, you want to know which of these, are these models equivalent or can they be distinguished? It was also interesting from a mathematical point of view because it turns out that a certain conjecture in operator algebra is called the Kahn embedding conjecture, if true, implies that these two models are equivalent. So the Kahn embedding conjecture is something about, approximating infinite dimensional objects with finite dimensional objects, and sort of by, a lot of deep math that implies this equivalence here. So where does our work come in? Well, if you think about this diagram here and these statements I made, well, if the tensor product model and the commuting operator model are equivalent, then MIP star will be equal to this other class, the commuting operator version of it. And so it'll have to lie in the intersection of these two complexity classes. So, this intersection in the Venn diagram. That's the class of decidable languages, R. And so since we showed that MIP star is equal to RE, that implies that, in particular, it cannot lie inside of R because R is distinct from RE. And therefore, these two models have to be different. So, we show that the answer to Tsearelson's problem is false and that there is a test that can distinguish between these two notions of entanglement. In fact, that test is just, our protocol for the halting problem. And moreover, by following these equivalences, you can show that this Kahn embedding conjecture is false. So that means that there's certain very pathological examples of algebras in operator theory. So just to clarify, these equivalences were sort of known already, and our main contribution here is showing this complexity result. And from that, these things follow. So, okay, now I'm going to close with the future directions. So, I'm broadly interested in many areas in quantum complexity theory, but these are just a few things, directly related to this work. So one direction that I think is very interesting is that I said that, MIP, the study of MIP had many consequences for complexity theory and cryptography. Can we do a similar thing with MIP star? And to what extent can these ideas be used to say things about quantum hardness of approximation or verifiable quantum computation, delegations of quantum computation, and so on? The other direction that I think is very interesting is, expanding on these connections to math and physics. There's potential for contributions to problems in group theory, representation theory, also understanding the techniques that were used in these proofs sort of in a mathematical language, I think would be helpful for future progress. So I think there's a lot of exciting things to do there. So that concludes my talk, and thank you very much for listening.
Maybe I just clap. So I don't know how it works. Yeah, if you have a question, raise your hand in the chat and I'll call on you. In the meantime, let me ask one question. So do you have any idea of what the, let's say, key technical piece is that sort of was missing in, for instance, I mean, you as you said, sort of this argument in particular shows that one can, so there exists these kind of pathological operator algebras that were that sort of don't have a nice finite dimensional approximations. So one possibility might be just that sort of operator algebraists are not good at building counterexamples of the type that in computability theory, how to do things like programs that obtain their own source code and then do something, whatever. But then you're also using lots of techniques from PCP theory and sort of this question compression. Do you have some sense of what is the key sort of technical thing that might be extracted out from this, from their perspective?
Yeah, I think it's not entirely clear yet. Like I don't feel like there's like one particular element that stands out. Like I think there are a couple ingredients. Like one is, as you said, like this algebra. Like if you convert our game into an algebra, it's like an algebra with like a very weird sort of self-recursive structure that maybe would not have occurred to computer science, to an algebraist who was not thinking about Turing machines, because like it really does come from Turing machines. The PCPs play an important role. Another thing that's an important role, I think, is like it's sort of like, I mentioned that we had this test for EPR pairs. Like there was first like a test for n EPR pairs, and then we were able to prove it to 2 to the n EPR pairs. And really that like quantitative difference between n and 2 to the n was sort of, it made a huge difference because, ultimately, we showed this result by this like recursive, like, chaining together this like compression idea many times. And the only way you can get like a savings every time you do this compression is that you need to be able to test for a super polynomial number of EPR pairs. So I guess I'd say that like these like very quantitative facts about like, in their language that would be saying there's a certain algebra that only has representations of like a certain dimension or higher. Like there's a family of algebras with representations that only have dimension 2 to the n or higher. Like the quantitative details of like how those dimensions scale were actually very important to the qualitative picture at the end.
Yeah, thanks. Raj, you have a question?
Yeah, Anand, that was a great talk. Congratulations on the big result. So my question is something that and also asked your collaborator Henry, and this is having to do with the implications for physics. So it's great that your result has implications for both mathematics and physics. And since you're a physicist, what have you seen in terms of the implications of how physicists have decided in terms of using, you mentioned the tensor product versus commuting operators way of, doing physics, quantum physics. So have there been repercussions of the result on physicists, the way that they view, their world?
Good. So I think we're still trying to work that out right now. So ideally what we'd like to have is, okay, what would be the gold standard of what to have is sort of like a Bell test kind of experiment where you could actually do the experiment, and moreover there'd be some reasonable physical theory where we could like write down what the strategy is that achieves a violation. So that way we could imagine like doing this in the real world and like certifying that we actually live in an infinite dimensional commuting operator world. So essentially what we get with this is just the first part. We have an experiment that conceivably could be done. We don't have a realistic physical model for how to actually succeed in the experiment. We just have, like an abstract like operator algebra that succeeds. And to make that work seems a little bit tricky because at least like the most natural candidate you might consider is an algebraic quantum field theory to realize this. And a lot of algebraic quantum field theories have something called the split property, which implies that, if I understand it correctly, it implies that whenever you're dealing with two space-time regions that are not touching, so they have some like gap between them, then you can approximate them by the tensor product model. And so to really exhibit this sort of separation, you need something that's either not an algebraic quantum field theory or something, an AQFT on some like kind of bizarre space-time or like something that I haven't come across yet. That said, I'm not an expert on these things. We haven't like directly asked any like, AQFT people, so maybe they just know of examples, but that's the impression I get right now. So there's definitely some work to be done to like, bring this down to the physics like realistic level.
Great, thanks.
Sure.
By the way, I just wanted to mention because that there was another similar sort of conjecture in the foundations of quantum physics, this Katterson-Singer problem, that you would also say that it's perhaps uninteresting because it involves states that require an infinite amount of energy to prepare. Now that conjecture was also resolved by computer scientists positively, but the point that despite seeming sort of like something like infinite dimensional, that work on that conjecture has already led to all kinds of stuff, including your colleague Cheyenne, who has used it to great effect to design algorithms. So, yeah, this kind of stuff is even like infinite dimensional things, because like Anand was saying that sort of like this is basically there's a quantitative scaling behind sort of the finite versus infinite dichotomy there. Is that a correct summary
Yeah,
of something?
I think that yeah, I think that would be that sounds accurate. I definitely like one thing that's interesting is to compare this with Caddis and Singer is that like I think they're they already knew before the computer scientists like got involved, there was like a nice reformalization of the problem in terms of like finite dimensional vectors. And it would be nice, I don't know to what extent like you could state this like Kahn problem in a way to like remove all of the operator algebras from it, and like really abstract it out. But be interesting to see. Like another thing that I think is kind of fun is like now this is like two problems in operator algebras that have sort of CS techniques have helped solve, and like I think there's like at least one more like big open problem there, like it's like the free group on 2 versus 3 generators or something, like whether these are different, like the dissociated algebras are different, and it would be wonderful if we could like say something about that problem too.
Okay,
Great.
let's
Thanks.
take any further questions offline. Thanks again, Anand, for an awesome talk.
Thanks.